I would imagine that to this point, when we've been talking about the motion of planets, you've had in your mind the idea that they are orbiting around the sun due to gravity. The sun has gravity. That's a fact that we all know, right? We know from an early age, but that wasn't always true. There wasn't really a physical world cause of what the planets were doing in space. Not until Isaac Newton gave us an answer to that question. You could say that up to that point, the cause of the motion of the planets was really religious based, that they moved that way because God had designed the universe so that they moved that way. And that's what Kepler was ultimately trying to figure out, was what was the design. He wasn't really thinking of it as a mechanical system that was obeying laws of nature so much as a celestial architecture that had been designed to function in a certain way. Now, Newton was also very religious. This is Newton pictured on the right. But he wasn't satisfied with that as an answer. He was convinced that there has to be some basic underlying principles that guide the motions of the planets. And so he wanted to understand that mechanics at a very deep level. At his time, in his current time, or in his time, I should say, there were no such mechanics. There were no laws of physics that had been written down that he could think about the universe from that perspective. So you have to take yourself out of the present and put yourself into that time where the laws of physics are not intuitive. They're not part of the fabric of life. When you move around in the world, you probably have a Newtonian view of things. Things move because there's forces on them, forces push. But this is before Newton had come up with these ideas. And so the reason why things moved, the causes for them, was not given a mechanical description. It was Newton who started that. Now, one of the hardest things to wrap your mind around is that, because it's so ingrained in us, that the idea of gravity was something that happened on Earth, and it wasn't the same thing that was happening with the planets in orbit around the sun. Those were two separate things. There was the motion of the planets, and then there was gravity on Earth. They were different, completely different. It took a pretty ingenious thought experiment by Isaac Newton to connect those two things together. And so that's what's being illustrated in the picture. He imagined someone standing at the top of a mountain on the earth. This is one of his, or a copy of one of his original drawings. He imagined standing on a mountain on the earth and throwing things off of it. Now, everybody at the time knew that when you threw something around the earth, it would fall back to the ground, and it would take this parabolic trajectory back to the ground, this curved path back to the ground. Gravity brought it back to the ground. But if you throw it faster and faster, it projects farther and farther. And if you take that to its logical conclusion, which is what Newton did, you could imagine throwing things fast enough so that they would circle all the way around the globe and then land right behind you. Right? Because what's happening when you throw something? It is falling to the ground. The faster you throw it, the farther it projects before it hits the ground. If you throw it fast enough, it would circle the entire globe before hitting the ground. Okay, so there's some things you have to set aside. You have to ignore air resistance and any sort of drag forces happening on the ball or object or whatever is being thrown. But let's say you do that. You've evacuated all the air, so there's nothing else stopping it. You throw the ball from the top of the mountain. If you threw it fast enough, it would circle around the globe and land right behind you. Well, if you threw it just a little bit faster, once it got to the point behind you, it would basically be in the same state as when it left your hand, moving at some speed, parallel to the ground. And so if you just stepped out of the way, it should keep going and going and going around and around in a circle. And what Newton realized is that's what an orbit is. An orbit is an object just in perpetual free fall. It's continuously falling to the ground. So the object leaves here, it goes around, it's constantly trying to fall to the ground, but it's also projecting forward, and it never makes its way to the ground before it gets back to the starting point. And so this just repeats over and over again. Now, things that are going faster, they're going even faster than that, they would just project onto bigger ellipses. And so you'd get bigger and bigger orbits. So he made this connection. Orbits are essentially perpetual free fall, which means that planets are in orbit because of the gravity of the sun. And so the next thing he did was to develop an entire framework for analyzing problems like this, which we now call classical physics. He essentially invented that field of study. He published a work called the Principia, which is one of the most famous works of science in all of history, arguably the most influential and significant works of science in all of history. It invented the entire field of physics, which gave us a fundamental way of analyzing all sorts of scientific problems. In all of the areas of science are affected by this work. And in that, the foundation was the laws of motion. Now, we don't need to know all the details of the laws of motion, but there are things like an object in motion will stay in motion until it's acted upon, that force is mass times acceleration, and that for every action there's an equal and opposite reaction. Those are the three fundamental laws of motion. But from our perspective, what they do is they quantify this concept of force that to that point had never been quantified. So when we think of force as something pushing on something else, Newton made it into something that you could calculate, and he related it to the motion of objects. And then he attached that to his ideas about gravity and developed a law of gravity. And then from his calculations, he was able to show that Kepler's laws all came from this basic fact, that orbits were the result of the gravity of the sun. And that's really powerful because Kepler's laws were essentially based on observational data. It's saying that this describes what we see in the sky. This mathematical relationship describes what we see in the sky. And then Newton said, if you make this assumption that gravity is causing it, and gravity works in this specific way, we find that these equations follow naturally from it. So what he did was really, really powerful, and there were some slight modifications to Kepler's laws. Namely, he made them more general. What Kepler found was very specific to the sun and our solar system. Newton showed that this would happen for any masses. It could be the Earth and the Moon, it could be the sun and the Earth, it could be the black hole at the center of the galaxy and our solar system. It would work for any pair of masses and any orbit is going to work in this way. And so he developed his own version of Kepler's third law, which looks like this up here. So there's two masses involved. The big one, or usually there's a bigger one and a smaller one. And that is an additional factor that goes into the calculation. Now for Kepler, the mass of the sun was so much bigger than the mass of any other planet that it was insignificant. So if you measure mass in units where the sun's mass is called 1, then this number here in parentheses would just be a 1. And so you get Kepler's third law as he wrote it. But with Newton's version, you can adapt it to any pair of masses that you want. So stars, planets, asteroids, anything with a mass that will be in orbit would obey this version of Kepler's third law. And so it's this idea here that we'll use in the Weighing Jupiter lab, because Jupiter is like a mini solar system. It has moons orbiting around it. And so we can calculate the mass of Jupiter by measuring the period and semi-major axis of the moons in orbit around it. All right, so what Newton's work did was gave us an explanation, like a true explanation for why the planets were moving the way they did. And it had a huge effect on the scientific community, but also the broader cultural world as well. Newton was very influential to a lot of writers and artists at the time, and one of his closest contemporaries was Alexander Pope. And so I've included a poem here by Alexander Pope that gives a little insight into how he saw the contributions of Newton's work and the effect that they had on their thinking at the time. And so one of the homework questions actually asks you to read this and to think about what it means and reflect on it. So I won't say too much about it here to bias your answers, but I'm interested to see what you come up with.